Hello dear students, all of you welcome to Vidyan classes. It is the third lecture on relations and functions. Today we will discuss important memory tips in lecture number 2, identity relation, equivalency relation and problem discussion on level 1, that means board level. Important memory tips in lecture number 2. In lecture number 2, we have discussed types of relation: replacive, symmetry, transitive, antisymmetric, partial ordering and total ordering. But there exist four relations, that is replacive, symmetric and transitive and antisymmetry in your course. What is the replacive relation? First point, the relation capital R subset or equal to across A, that means R is the relation on A. The relation on A, that is R subset or equal to across A, is called reflexive if excess order pair belongs to R for all x belongs to A. The relation capital R subset or equal to across A, that means R is a relation on A, is called reflexive if x related to x or excess order pair belongs to R for all x belongs to capital A. Second point, symmetry relation. The relation capital R subset or equal to across A is called symmetric if for xy belongs to R, that implies yx order pair belongs to R. The relation R on A, that means R subset or equal to across A, is called symmetry if for xy belongs to R, that implies yx belongs to R. Third point, transitive. The relation capital R subset or equal to across A is called transitive if for xy belongs to R, yz belongs to R, that implies xz order pair belongs to R. The relation capital R subset or equal to across A, that means R is the relation on A, is called transitive if for xy belongs to R, xy order pair belongs to R, yz order pair belongs to R, that implies xz belongs to R. Clear? Fourth point, it is symmetric, it is a transitive. The relation capital R subset or equal to across A is called antisymmetric if xy belongs to R, Yx belongs to R, that implies x is equal to y. xy belongs to the relation capital R subset or equal to across A is equal to antisymmetric if xy belongs to R, yx belongs to R, that implies x equal to y. xy belongs to R, xy belongs to R, yx belongs to R, represent the relation is symmetric. Here xy belongs to R, yx belongs to R. So antisymmetry relation implies the relation is symmetric. Antisymmetry, note, antisymmetry implies symmetry. Antisymmetry implies symmetry. As xy belongs to R, yx also belongs to R, it represents the definition of symmetric. So antisymmetry implies symmetry. Clear? Antisymmetric, but the converse is not true. Antisymmetry implies symmetry, but the converse is not necessarily true. Clear? Clear? The relation R is reflexive if x order pair belongs to R. For all x belongs to A, the relation R is symmetric. If for xy belongs to R, that implies yx belongs to R. The relation R is transitive. For xy belongs to R, yz belongs to R, that implies xz order pair belongs to R. The relation R is antisymmetric if xy belongs to R, yx belongs to R. It is the condition of symmetry, which implies x equal to y. Note, antisymmetric implies symmetric. In antisymmetry, the antisymmetry relation satisfies the definition of symmetry. So antisymmetric implies symmetric. Clear? Okay. Next, identity relation. What is identity relation? The relation capital R subset or equal to A cross A. That means R subset equal to A cross A implies R is a relation on A. The relation R subset equal to A cross A is called identity relation if XX order pair belongs to R for all X belongs to A. The relation capital R subset or equal to A cross A, that means R is a relation on A, is called identity relation if XS order pair belongs to R for all X belongs to capital A. It is also denoted by IA. IA means identity relation on A. So we can write, so R is equal to IA, which is same as set of XX order pair such that for all x belongs to capital A. Excess order pair belongs to IA or excess order pair belongs to R. R is the relation. What type of relation? Identity relation. In identity relation, the x coordinate and y coordinate are same. Example, find the identity relation on A is the set containing 3, 7, 9. Find the identity relation on the set containing 3, 7 and 9. By definition, identity relation IA is the set of excess order pair for all x belongs to A. For all x belongs to A, here x represent 3, 3, 3 order pair, 3 belongs to A, 3, 3 order pair belongs to IA. 7 belongs to A, 7, 7 order pair belongs to IA. 9 belongs to A, 9, 9 order pair belongs to IA. So, answer, the identity relation on A is the collection of excess order pair such that for all x belongs to A, which is same as set of 3 belongs to A, 3, 3 order pair belongs to IA, 7 belongs to A, 7, 7 order pair belongs to IA, 9 belongs to A, 9, 9 order pair belongs to A. Is the identity relation on A. Excess order pair belongs to IA. For all x belongs to A. For all x belongs to A means x represent 3, x represent 7, x represent 9. Clear? Okay. Next. Equivalence relation. What is the equivalence relation? The relation R subset equal to A cross A is said to be equivalence if it is reflexive, symmetric and transitive. The relation capital R subset or equal to A cross A. That means R is a relation on A is called equivalence relation. Is called equivalence relation. If it is reflexive relation, symmetric relation and transitive relation. If it is reflexive, symmetric and transitive relation. Here, the relation capital R subset or equal to A cross A is called equivalence relation if it is reflexive, symmetric and transitive relation. Example, Find the smallest and largest equivalence relations on A is a set containing 3, 4, 5. Find the smallest and the largest equivalence relations on capital A. Find the smallest and the largest equivalency relation on A. Equivalency relation means the relation which is replacive, symmetric and transitive. First answer, first bit, smallest equivalence. Let R1 is the set of 3 order pair, 4 order pair, 5 order pair. Is the smallest equivalence relation on A. As it satisfies the definition of reflexive, symmetric and transitive. Reason R1 is the set of 3 order pair, 4 order pair, 5 order pair is the smallest equivalency relation on A, as it satisfies the definition of reflexive, symmetric and transitive. What is the reason? R1 is the set of 3 order pair, 4 order pair, 5 order pair, which is same as 3 order pair, 3 order pair, 3 order pair, 4 order pair, 4 order pair, 4 order pair, 5 order pair, 5 order pair, 5 order pair. Since repeated elements in a set, that is a relation is a set, are not allowed. So this set is same as this set. It is satisfied the definition of reflexive, symmetric, transitive. What is reflexive? For all x to the given set, x's order pair belongs to R. 3 belongs to A, 3 belongs to A, 3 order pair belongs to R1. 4 belongs to A, 4 order pair belongs to R1. 5 belongs to A, 5 order pair belongs to R1. So R1 is reflexive. R1 is also symmetric. What is the definition of a symmetric? XY order pair belongs to R, that implies YX order pair belongs to R. 3-3 order pair belongs to R1. It is reverse order pair, that is 3-3 order pair belongs to R1. 4-4 order pair belongs to R1. Its reverse order pair 4-4 order pair also belongs to R1. Similarly for 5-5 order pair. So the relation is symmetry. R1 is also transitive. Why? What is the definition of transitive? The relation R is said to be transitive if XY order pair belongs to R, YZ belongs to R, and XZ, that implies XZ belongs to R. 3-3 order pair belongs to R1, XY order pair belongs to R1, YZ order pair belongs to R1, that implies XZ, that is 3-3 order pair belongs to R1. So R1 is satisfies the definition of a transitive. XY order pair belongs to 4-4 or X to Y, Y to Z, X to Z, that is 4-4. 4-4 order pair belongs to R1, that means XY belongs to R1, YZ belongs to R1, XZ, that means 4-4 belongs to R1. So R1 is transitive. Similarly, we can say for 5-5 order pair, the relation R is transitive if XY order pair belongs to R, YZ order pair belongs to R, that implies XZ belongs to R. So R1 is transitive. R1 satisfies the definition of reflexive, symmetric, and transitive. So R1 is the smallest equivalence relation on capital A. Clear? Second, find the largest equivalence relation. Second bit, R2 is equal to A cross A is the largest equivalence relation on A is the largest equivalence relation on A, since all relations are derived from A cross A. Since all relations are derived from A cross A. From A cross A, we can find out it gives reflexive relation, A cross A gives symmetry relation, and A cross A gives transitive relation. So R2 is equal to A cross A is the largest equivalence relation, since all relations are derived from A cross A. Relation is the subset of a Cartesian product. A cross A contains reflexive relation, A cross A contains symmetry relation, A cross A contains transitive relation. It is the largest relation on A, which is the equivalence. Clear? No doubt? Next question. So that if R is an equivalency relation on capital X, then dom of R is equal to range of R, which is equal to X. R is an equivalency relation. Given capital R is an equivalence relation on capital X, implies R subset or equal to X cross X. This implies R is the relation on X. By definition of equivalence relation R is a reflexive symmetric and transitive relation. Clear? R is an equivalence relation on X, that implies R subset or equal to X cross X. By definition of equivalence relation, R is reflexive, symmetric and transitive relation. Since R is reflexive, for all X belongs to capital X, XX order pair belongs to R. It is the definition of a reflexive relation. So, R is equal to set of XX order pair, such that for all X belongs to capital X, XS order pair belongs to R, for all X belongs to capital X. So, R contains set of XS order pair where X is any element in capital X. Domain of R which is same as dom R. It is shortly written as dom R. What is domain R? The set of all first members of the order pairs in R. It is the set of all first members of the order pairs in R. What is the first member? X. So that X belongs to capital X's order pair belongs to R. It is the definition. The set of all first members of the order pairs. It is the first member. It is the second member. The set of all first members of the order pairs in R. For all X belongs to capital X, which is same as What is X? Any element in capital X. So it is represent X. Clear? What is X? X is any element in capital X. So this set is equal to capital X. Range of R, which is same as RNG R. Range of R. What is range? The collection of second members of the order pairs in R. What is the second member? That is X. So that X is order pair belongs to capital R. What is X? X is any element in capital X. So it is represent capital X. Clear? Okay. Therefore, DOM R is equal to range R is equal to capital X. Hence, good. Note down. Next question. Test whether the following relations is reflexive or symmetric or transitive. Solution. The relation capital R on Z, Z means set of integers, is defined by R is equal to set of mn order pair so that m minus n greater than 7 or equal to 7. Which implies mn order pair belongs to R. Mn order pair belongs to R so that m minus n greater than 7 or equal to 7. So that m minus n greater than or equal to 7. Clear? Mn order pair belongs to R so that m minus n greater than or equal to 7. The relation is true if this condition is satisfied. We have to test the relation is reflexive or symmetric or transitive. Let M, N, P be three elements belongs to Z set. That means set of integers. Test for reflexive. What is the definition of reflexive? For all x belongs to a, x's order pair belongs to R. Then R is called reflexive. For all M belongs to Z. Here the given set is Z. M minus M is equal to 0. 0 greater than 7 is false. 0 equal to 7 is false. Is a false statement. Implies M order pair does not belongs to R. Now we have for all for all m belongs to Z set, order pair does not belongs to R. Therefore, R is not reflexive. The relation is true. Mn order pair belongs to R if this condition is satisfied. That means the difference is greater than 7 or equal to 7. Here, for reflexive, x equal to y. X means it is m and y means n. M equal to n. M minus m equal to 0. 0 greater than 7 is false or 0 equal to 7 is false. So it is a false statement. Implies order pair does not belongs to R. Now we have for all m belongs to Z set, m order pair does not belongs to R. So R is not reflexive. Clear? Okay. Test for symmetry. What is the definition of symmetry? X related to y, that implies y related to x. So that R is symmetric. Mn related to Mn order pair belongs to R, that implies Nm order pair belongs to R, so that R is symmetric. Mn order pair belongs to R, so that m minus n greater than or equal to 7, which implies n minus m is less than or equal to minus 7. Multiplying minus both the sides, greater than will be less than, greater than will be less than, n minus m less than equal to minus 7. N minus m greater than equal to 7 is a false statement. Clear? N minus m is less than or equal to minus 7. N minus m greater than 7 or equal to 7 is a false statement. N minus m greater than equal to 7 is a false statement, which implies Nm order pair does not belongs to R. Now we have Mn order pair belongs to R implies Nm order pair does not belongs to R. So R is not symmetric. Clear? Clear? Mn order pair belongs to R, so that m minus n greater than equal to 7, which implies n minus m less than equal to minus 7, which implies n minus m greater than equal to 7 is a false statement. If this condition is satisfied, we can write Nm order pair is a false statement. Nm order pair does not belongs to R. Mn order pair belongs to R, Nm order pair does not belongs to R, so R is not symmetric. Clear? Test for transitive Mn order pair belongs to R and Np order pair belongs to R. What is the transitive relation? Mn order pair belongs to R, Np order pair belongs to R, implies this Mp order pair belongs to R, then the relation is said to be transitive. Mn order pair belongs to R implies this M minus n greater than equal to 7. Mn order pair belongs to R such that M minus n greater than equal to, since Mn order pair belongs to R, M minus n greater than equal to 7, Np order pair belongs to R, so n minus of p greater than equal to 7. Clear? M minus n greater than equal to 7, n minus of p greater than equal to 7. Adding the two conditions, which implies this m minus of p greater than equal to 14. Clear? 14 is greater than 7, which implies this m minus of p greater than 7, which implies this if Mn belongs to R, that means M related to N. If this condition is satisfied, what are the conditions? Either M minus N greater than 7 or M minus N equal to 7. Here M minus P greater than 7 is true. So MP belongs to R. Mn order pair belongs to R, Np order pair belongs to R, that implies Mp order pair belongs to R. There are two conditions, either greater than 7 or equal to 7. It satisfies the greater than condition. Mp order pair belongs to R. Now we have Mn order pair belongs to R, Np order pair belongs to R, implies this Mp order pair belongs to R. So R is transitive. So the relation defined by is not reflexive, not symmetric, but transitive. So in general R is not reflexive, not symmetric, but transitive. In general, the relation R is not reflexive, not symmetric, but transitive. Clear? Note down. Next question. Test whether the following relation is reflexive, symmetric, or transitive. The relation is defined by R is equal to set of Mn order pair so that 2 divides m plus n on z. R is a relation on z. Solution: R is a relation on z defined by R is equal to set of mn order pair such that 2 divides m plus n. R is a relation on Z defined by R is equal to set of mn order pair so that 2 divides m plus n. Clear? Mn order pair belongs to R implies this. Mn order pair belongs to R such that 2 divides m plus n. Mn order pair belongs to R so that 2 divides m plus n. We have to test the relation is reflexive or symmetric or transitive. Let m, n, p be 3 integers. That means mn p belongs to Z set. Test for reflexive. What is reflexive? For all m belongs to Z set, mn order pair belongs to R, so that R is reflexive. For all m belongs to Z set, 2 divides m plus n. 2 divides m plus n. For reflexive, x coordinate and y coordinate are same, which implies as 2 divides 2m. Is it true? That is, order pair belongs to R. Now we have for all m belongs to Z set, order pair belongs to R. So R is the reflexive. Clear? For all m belongs to Z, order pair belongs to R, so R is the reflexive. Clear? Okay. Test for symmetry. Mn order pair belongs to R. Mn order pair belongs to R, so that 2 divides m plus n, which implies this 2 divides m plus n, 2 divides n plus n. Clear? 2 divides m plus n. In this case, mn order pair belongs to R. Now we have 2 divides n plus m implies as nm order pair belongs to R. Now we have mn order pair belongs to R. That implies nm order pair belongs to R. So the relation capital R is symmetric. Mn order pair belongs to R, Nm order pair belongs to R, so R is the symmetry. Test for transitive. For transitive, at what condition R will be transitive? Mn order pair belongs to R, Np order pair belongs to R, implies this MP order pair belongs to R, then R is the transitive. Mn order pair belongs to R and Np order pair belongs to R. So that Mn order pair belongs to R, so that 2 divides M plus N. So that 2 divides M plus N and 2 divides N plus P, which implies 2 divides M plus N. M plus N is equal to 2K and N plus P is equal to 2K1. 2K2, where K1, K2 belongs to Z set. 2 divides M plus N, so M plus N is equal to 2K1 and 2 divides N plus P, so N plus P is equal to 2K2, where K1, K2 belongs to Z. Adding the above two statements, M plus N plus N plus P is equal to 2K1 plus K2, which is equal to 2K3, where K1 plus K2 is equal to K3 belongs to Z set. Clear? Mn order pair belongs to R, implies this 2 divides M plus N. Np order pair belongs to R, implies this 2 divides N plus P, which implies this M plus N, 2 divides M plus N is equal to K1, N plus P is equal to K2, K1, K2 belongs to Z set. Adding the above two statements, we have M plus P is equal to 2K3 minus 2N, which implies M plus P is equal to 2K3 minus N, which implies M plus P by 2 is equal to K3 minus N, which implies 2 divides M plus P is equal to K4. K4 belongs to Z. Since K3 is an integer and N is also an integer, difference is an integer. 2 divides M plus P, that implies MP order pair belongs to R. Now we have Mn order pair belongs to R, Np order pair belongs to R, that implies Mp order pair belongs to R, therefore R is transitive. Clear? The relation defined by is reflexive, also symmetric and transitive. In general, R is equivalence on equivalence relation. R is equivalence relation on Z. R is equivalence relation on Z. Clear? Next question. Test whether the following relations is reflexive, symmetric or transitive. The relation is defined by R is equal to set of mn order pair so that m by n is a power of 5 on non-zero integers. Given R is a relation, R is a relation on Z minus set of 0. That means non-zero integers. R is a relation on Z minus set of 0 and defined by R is equal to set of mn order pair so that m by n is a power of 5. Implies mn order pair belongs to R so that m by n is a power of 5. If this condition is satisfied, m related to n or mn order pair belongs to R. Here, mn order pair belongs to R if m by n is a power of 5 or m by n can be expressed of the power of 5. We have to test the relation is reflexive or symmetric or transitive. Let m, n, p be 3 non-zero integers belongs to Z minus set of 0. Test for reflexive. For all m belongs to Z minus set of 0, m by m is equal to, for reflexive, m equal to n, which is equal to 1, which can be written as 5 to the power 0. 1 can be expressed of the form of, that is power of 5. Implies m by m is a power of 5. That is order pair belongs to R. Clear? Now we have for all m belongs to Z, order pair belongs to R. So R is reflexive. For all m belongs to Z, order pair belongs to R. So R is reflexive. It is the definition of a reflexive. Test for symmetry. A main order pair belongs to R, so that m by n is a power of 5. M by n can be expressed of the form 5 to the power something. Let m by n is equal to 5 to the power k. M by n can be expressed as 5 to the k. M by n is a power of 5, which implies n by m is equal to 5 to the minus k. N by m is a power of 5. That is, n by m is a power of 5. N by m is a power of 5 implies Nm belongs to R. M by n is a power of 5. In this case, Mn order pair belongs to R. N by m is a power of 5 implies Nm order pair belongs to R. Now we have Mn order pair belongs to R. That implies Nm order pair belongs to R. It is the definition of a symmetric. So R is a symmetric. Clear? Next, transitive. A main order pair belongs to R. That is, m by n is a power of 5, and np order pair belongs to R, such that n by p is a power of 5. Since Mn order pair belongs to R, so that m by n is a power of 5. Mn order pair belongs to R, so that m by n is a power of 5. Np order pair belongs to R, so that n by p is a power of 5. Let m by n is equal to k 5 to the power k1, n by p is equal to 5 to the power k2. Implies m by n into n by p is equal to 5 to the power k1 into 5 to the power k2, which is equal to 5 to the power k3, where k1 plus k2 is taken as k3, which implies m by p, nn cancel, which is equal to 5 to the power k3, which implies m by p is a power of 5. M by p is a power of 5. MP order pair belongs to R. Mn order pair belongs to R if m by n is a power of 5. Here m by p is a power of 5 implies MP belongs to R. Now we have Mn order pair belongs to R, NP order pair belongs to R, that implies MP order pair belongs to R. It is the definition of a transitive. So R is transitive. Now we have R is reflexive, R is symmetric, and R is transitive. In general, we can say the relation defined by on z minus theta of 0 is an equivalence relation. Clear? Note down. Next question. The relation R on Z is defined by R is equal to Mn order pair, so that Mn is divisible by 2. Solution. The relation R on Z, Z means set of integers, is defined by, the relation R on Z is defined by R is equal to set of Mn order pair, so that Mn is divisible by 2. Mn order pair belongs to R, so that Mn is divisible by 2. We have to test the relation is reflexive or symmetric or transitive. Test for reflexive. The relation R is reflexive if for all m belongs to Z, mm order pair belongs to R. For all m belongs to Z set, that is set of integer. For reflexive m equal to n is equal to m square is divisible by 2 is a false statement. It is not true for all m belongs to Z. Partially it may be correct. Partially correct is not correct. For example, m is equal to 3. m square is equal to m into m is equal to m square is equal to 9 is not divisible by 2. Implies mn divisible by 2, mn order pair belongs to R. Implies order pair does not belongs to R. So for all m belongs to Z, m order pair does not belongs to R. Therefore, R is not reflexive. Here, partially it may be correct. In general, it is not true. Partial correct is not correct. For all m belongs to Z, order pair. For all m belongs to Z, order pair does not belongs to R. So R is not reflexive. Test for symmetry. Test for symmetry. Mn order pair belongs to R, such that Mn order pair belongs to R, such that Mn is divisible by 2. Mn is divisible by 2. That implies Nm is divisible by 2. Mn is divisible by 2 implies that Nm is divisible by 2 is true. Implies Nm order pair belongs to R. Clear? Now we have Mn order pair belongs to R, that implies Nm order pair. Mn order pair belongs to R, that implies Nm order pair belongs to R. It is the definition of a symmetric. Therefore, R is symmetric. Clear? R is symmetric. Test for transitive. Clear? Test for transitive. For transitive, Mn order pair belongs to R, Np order pair belongs to R, that implies Np order pair belongs to R, so that the relation R is transitive. Mn order pair belongs to R and Np order pair, let M and P belongs to Z set. M and P are 3 integers. Mn order pair belongs to R and Np order pair belongs to R, so that since Mn order pair belongs to R, Mn is divisible by 2 and Np order pair belongs to R, Np is divisible by 2. Clear? Mn order pair belongs to R, Mn divisible by 2 by the given statement. Mn is divisible by 2, Mn order pair belongs to R. Since Mn is divisible by 2 implies as Mn is equal to 2k1 and Np is divisible by 2, so Np is equal to 2k2, where k1, k2 belongs to Z set. Since Mn is divisible by 2, we can write Mn is equal to 2k1, Np is divisible by 2, so we can write Np is equal to 2k2, which implies Mn into Np is equal to 2k1 into 2k2, that is equal to 4k1 into k2, which is equal to 4k3, where k1, k1 into k2 is equal to k3 belongs to Z set, which implies as Mp is equal to 4k3 divided by n square is divisible by 2 is a false statement. Partially it may be true, but in general it is not true. Partially correct is not correct. For example, m is equal to 3, n is equal to 2 and p is equal to 5. Mn is equal to 6 is divisible by 2. Np is equal to 10 is divisible by 2 by 2. But Mp is equal to 15 is not divisible by 2. Clear? Mp is divisible by 2 is a false statement. Clear? Implies as Mp order pair does not belongs to R. Mn is divisible by 2, Mn order pair belongs to R. Since Mp is not divisible by 2, is divisible by 2 is false or not divisible by 2, Mp order pair does not belongs to R. Now we have Mn order pair belongs to R, Np order pair belongs to R, implies this Mp order pair does not belongs to R. Clear? Therefore, R is not transitive. In general, R is not reflexive. In general, the relation R defined on Z is not reflexive and not transitive but it is symmetric. In general, the relation R defined on Z is not reflexive and not transitive, but it is symmetric. Clear? Next question. The relation R on this set defined by R is equal to set of Mn order pair such that 3 divides M minus N. Solution. The relation R on A is defined by R is equal to set of Mn order pair such that 3 divides M minus N, where A is equal to set of 1, 2, 3, 10. We have to test the relation is reflexive or symmetric or transitive. Test for reflexive. Mn order pair belongs to R if 3 divides M minus N. For all M belongs to A means the set of 1, 2, 3 up to 10. M minus 3 divides. For all M belongs to 3 divides 0 is true. Which implies as 3 divides M minus M is true. For all M belongs to A, 3 divides 0 is true. 0 is replaced by M minus M. 3 divides 0 minus 0. So, for all M belongs to capital A, MM order pair belongs to R. Mn order pair belongs to R if 3 divides M minus N. Here 3 divides M minus M. So MM order pair belongs to R. Therefore, R is reflexive. Clear? 3 divides M minus N implies Mn order pair belongs to R. Here 3 divides M minus M is true. So for all M belongs to M, MM order pair belongs to R. It is the definition of a reflexive. Therefore R is reflexive. Test for symmetric. Mn order pair belongs to R such that three divides M minus N. Mn order pair belongs to R, so that 3 divides m minus n, which implies this. 3 divides m minus n, which implies this. M minus n by 3 is equal to k. K belongs to Z, which implies this. N minus m divided by 3 is equal to minus k. Minus k belongs to Z set. Clear? Which implies this. 3 divides n minus m. 3 divides m minus n. That is 3 divides n minus 3 divides m minus n. Mn order pair belongs to R. 3 divides n minus m implies this. Nm order pair belongs to R. Now we have Mn order pair belongs to R. That implies Mn order pair belongs to R. That implies Nm order pair belongs to R. Therefore, it is the definition of symmetry. R is symmetry. Clear? Next, test for transitive. Let M, N and P belongs to A. Transitive. Mn order pair belongs to R and Np order pair belongs to R. So that 3 divides m minus n and 3 divides n minus p, which implies this. 3 divides m minus n and 3 divides n minus p. Vertical line is read as divides. 3 divides m minus n, 3 divides n minus p, which implies this. M minus n by 3 is equal to k1 and n minus p by 3 is equal to k2, which implies this. M minus n is equal to 3k1 and n minus p is equal to 3k2, where k1, k2 belongs to Z set. Now m minus n plus n minus p is equal to 3k1 plus 3k2, which is equal to 3k1 plus k2, which is equal to 3k3, where k1 plus k2 is equal to k3. K1, K2 are two integers. Sum of two integers is another integer. N cancel, which implies this. M minus of P is equal to 3K3, which implies this. M minus of P divided by 3 is equal to K. That implies 3 divides M minus P, which implies this. 3 divides M minus P. Done. Which is same implies this MP order pair belongs to R. Now we have Mn order pair belongs to R, Np order pair belongs to R, that implies Mp order pair belongs to R. Mn order pair belongs to R, Np order pair belongs to R, that implies Mp order pair belongs to R. What is this? What is this? It is the definition of a transitive. Mp. Therefore, R is transitive. In general, what is R? R is reflexive, R is symmetric, R is transitive. If a relation is reflexive, symmetric and transitive, then it is called an equivalence relation. In general, R is an equivalence relation on A. What is A? Set of 1, 2, 3 up to 10. Clear? Okay. No doubt. Next question. The relation on Z is defined by R is equal to set of Mn order pair so that M plus N is not divisible by 3. Solution. The relation on Z. Z means set of integers. The relation R on Z is defined by R is equal to set of Mn order pair so that M plus N is not divisible by 3. Mn order pair belongs to R so that M plus N is not divisible by. If M plus N is not divisible by 3, then M and N are related. Clear? Or Mn order pair belongs to R. We have to test the relation is reflexive or symmetric or transitive. Test for reflexive. What is reflexive? For all M belongs to Z set. If MM order pair belongs to R, then the relation is reflexive. For all M belongs to Z set, m plus m. For replacive, m is equal to n, that is equal to 2m is an even num. Even integer for all m belongs to z. 2m is an even integer which is not divisible by 3 is true. M is equal to 1, it is 2, M is equal to 2, it is 4. 4 is not divisible by 3. M is equal to 10, it is 20. Not divisible by 3. Clear? Implies yes. M plus M is not divisible by 3. M plus N is not divisible by 3. A main order pair belongs to R. M plus M is not divisible by 3. So MM order pair belongs to R. Now we have for all M belongs to Z, MM order pair belongs to R. Clear? Clear? It is true when the R is a relation when M plus N is not divisible by 3. Here M plus M is not divisible by 3. So MM order pair belongs to R. M N belongs to R if this term is not divisible by 3. Here M plus M is an even integer not divisible by 3. So the given statement is true. So MM order pair belongs to R. Now we have for all M belongs to Z, MM order pair belongs to R. So R is the reflexive. Test for symmetry. Mn order pair belongs to R, so that M plus N is not divisible by 3. Not divisible by 3. M plus N is not divisible by 3. Implies N plus M is not divisible by 3. N plus M is not divisible. M plus N is not divisible by 3. Mn order pair belongs to R. Implies Nm order pair belongs to R. Now we have Mn order pair belongs to R. Implies Nm order pair belongs to R. It is the definition of symmetric. Therefore, R is the symmetric. Clear? Okay. Test for transitive. Test for transitive. A main order pair belongs to R and NP order pair belongs to R. First you write let M and P belongs to Z set. A main order pair belongs to R and NP order pair belongs to R, so that a main order pair belongs to R implies this, so that M plus N is not divisible by 3 and NP order pair belongs to R, N plus P is not divisible by 3, which implies this. M plus N is not divisible by 3. M plus N not equal to 3K1. Since 3K1 is divisible by 3, since it is not divisible by 3, M plus N not equal to 3K1, N plus P is not equal to 3K2. K1, K2 belongs to Z set, which implies this M plus N plus N plus P not equal to 3K1 plus K2, which is equal to 3K3, where K1 plus K2 is equal to K3. Clear? Now, which implies this M plus P is not equal to 3K3 minus 2N, which implies this M plus P is not divisible by 3 is a false statement. Is a false statement. Is a false statement. Why? M plus N is not divisible by 3. N plus P is not divisible by 3. M plus P not equal to 3K minus 2N implies this M plus P is not divisible by 3. Why? For example, M is equal to 2, N is equal to 3, P is equal to suppose 10. M plus N, which is equal to 5, is not divisible by 3. N plus P, that is equal to 13, is not divisible by 3. But 2 plus 10 m plus p is equal to 2 plus 10 which is equal to 12 is divisible by 3. So m plus p is not divisible by 3 is a false statement. Now we have them, which implies MP is not divisible by 3 is a false statement. MP order pair does not belong to R. Now we have Mn order pair belongs to R. NP order pair belongs to R. But MP order pair not belongs to R. Therefore, R is not transitive. In general, R is not reflexive. In general, R is in general the relation R on Z defined by is not is reflexive and symmetric, but not transitive. R is reflexive, R is reflexive, R is symmetric, but R is not transitive. Clear? Okay, no doubt.